Hello dear friends, a great welcome to the series on Idea Statica member. Myself Jarajan P. This is tutorial number 39 and corresponds to part 2 of the tutorial 38. This part essentially covers the modeling of stiffness, analysis and interpretation of results. The problem statement is the same as that of tutorial 38 and do not require any explanation. So let me take you directly to the Idea Statica member. Let us proceed for the modeling of the stiffness. So first of all, let us straight away start with the design of the end stiffness. So it is not like that you straight away proceed for the design of the stiffness. You can straight away carry out an analysis without the end stiffness and come to a judgment whether they are really required or not. So for just for the illustration purpose, as you can see that I have just provided a small file here. So you can see here, I have carried out an analysis. Okay, so let me just go to the top of it. Okay, fine. So look here. Here you can see that I carried out an analysis without the end stiffener or without the what we call as a support stiffener. And here as you can see that if no stiffness would have been provided in the support, you can see that the strain distribution, there is an accumulation of the strain as expected at the support and the strain levels have gone up to even 15%. This is not allowed. Okay. And secondly, I also carried out an LBA, that's a linear buckling analysis without this support stiffener. And as you can see that here, the web of the plate girder, it buckles and the factor of safety it is just 1.3. Okay, and so first of all, though I have got a factor of safety of 30% as far as the buckling is concerned, from the material strength I don't have any safety because the strains have gone up to 15%. This prompts me to go ahead with the what we call as the modeling of the stiffness at the supports. So it is very important that you go ahead with some calculations and based on which you conclude that yes, a particular stiffener is very much required. So let me just take you to the modeling of the stiffness of the supports. So here you can see that so first of all, if you want to model the stiffness, you have to select the analyzed member, that's AM1, which I have selected. So accordingly, you can see that the color code of the member has changed. Now what you can do is that you can just press the operation, and in the operation you'll find that there is a transverse stiffener. Just click it. Okay, so you will find that yes, some stiffener it has automatically generated. So let me just take it. Okay, look here, it has created some stiffener. That's a default stiffener. Now what I will do is that I will create now two stiffness as concluded from my calculations. I will provide one at the leftmost edge and the other at the rightmost edge. Okay, so what you can do is you can go straight to, yes, this is an operation. It has created a transverse stiffener known as a stiff T1. Okay, now let us go on editing the parameters. So as it is a stiffener the support, I would provide a little bit larger thickness, that's a 12 mm, and you can see that I require it on both sides. And the material, so you can just put it as the same as that of the plate girder. So here you can say that you select it as S275, and the X position, that means what must be the position of this stiffener. So you can say that the X position you require leftmost edge. So let me keep it as a 0. Okay, now the inclination it is all 0, and the width I have kept it as by default. Okay, it is 0 means by default it occupies the full width of the plate girder. Okay, so I will just zoom it later. Now I want to have the same stiffener at the rightmost support. So what I will do is I will make use of a repeat count here. So you can just take it as 2, means that you want a copy at the other end as well. And what must be the gap? So the gap delta x. So delta x, obviously we know that we want it at the other end, so we have to keep it as 20,000. So this is 20,000. Okay, fine. And all other parameters you can keep just like that. So let me take you to the stiffener that is already modeled. Look here. Let me just take this. Okay, so this is the one stiffener. You can see that it is provided. Yes, this is one stiffener that is provided on both faces. right at the start of this plate girder, okay, and you can see that it covers the stiffness that is provided at the supports. It covers the full width of this plate girder, and obviously we have modeled a similar a similar stiffener at this support also, which you can see it from here, from this end. Just moved it down. Okay, so a similar stiffener has been provided here also, and you can see whether it is available on the other support also. Yes, it is available on both faces. So this means that our stiffener modeling at the support is over. So we have to make use of now the same procedure. So now let me check. So the support we have seen by our calculation, stiffness are required at the supports. We have provided it. Now we will make a small MNA, that's a material nonlinear analysis, as well as the LBA without the stiffness at the load application point. You know that there is a load of 500 kilonewton at this location and also at this location. So maybe that in some many of the cases the web may not be having the sufficient strength to take care of this load. So first let us investigate whether this is required, right? By sitting, okay, we have to perform some preliminary calculation, and also we can take the help of Idea Statica. So as I already told you, I investigated again. So you can say that here, yes, let me just go down. Yes, look here. I performed an analysis, okay, wherein no stiffeners are provided. Okay, no stiffeners are provided at the load points. So here you will find that I have not provided any stiffeners. So now looking into the factor of safety, I have got only a factor of safety of 1.15. That means it is about to buckle, right? So based on this criteria, I have decided, yes, I will provide two stiffeners, one at each concentrated load location. So let us go ahead for the same purpose. So just like the earlier one, what you do is you straight away select the member. Just a minute. Okay, select the member first. Okay, and then what you can do is you can go for the operation. It's the same this thing procedure. Go to the transfer stiffener. Then obviously here, as it's a load transfer, as it is a load carrying stiffener, I will provide a little bit larger one. That's a 12 again, and location will be the both sides, and the material will be keeping the same one, that is S275. And the X position, you know that the first stiffeners, the load location is 7000. We'll keep it as 7000. Alpha will be 0, and the width, what we can do is that we can reduce, we can make use of a smaller width here. We need not extend the stiffener throughout the flange width. That means we can keep, for example, say 150 mm. That should be good enough, because we have seen that as far as the buckling is concerned, it has passed it, but we have got a smaller margin. Now all this offset top and all, I won't extend it throughout. Now I want a similar stiffener. Want a similar stiffener, okay, at the second load point also. So to repeat it, you just put a 2 number. I want a copy of it. And now once you keep 2, it will ask you what is the distance at which. Obviously you know that the second load comes after 6000 mm. So keep it as a 6000. 6000, okay, fine. So this should automatically generate. Yes, you can see that, yes, it is already generated the 2 points. So let me just zoom it. Yes, okay, fine. So this is the stiffener, and if you see it from the other angle, let me just zoom in. This is good enough. Look here. Here you can see that the stiffener do not extend throughout the width, because we have provided only 150 mm. That is good enough for us. And you can also see that the same stiffener is also provided on the other side. Okay, so we have modeled very easily the stiffeners. Now the question is, at the prominent locations we have now provided the stiffness. Now the question is whether we need some other intermediate stiffness or not. So what you can do, similarly go ahead with an material nonlinear analysis and a buckling analysis without providing the internal stiffness, and see whether they are required or not. If and only if they are required, go for the modeling. Okay, and this is how we go step by step. This may take some time. See, obviously if you want an economical and an efficient solution, you have to spend some time, you have to spend some efforts. Okay, so let me just, so similarly what I did is, as I already told you, I carried out another analysis without this intermediate stiffness. Now let me just explain you what were the results. So look here. So here you can see that I did not provide any intermediate stiffener. That means a stiffener I have not provided next to the stiffener at the support. So my linear buckling analysis says that it did not have proper factor safety, or you can say that the factor safety is hardly, say, let me just say it is only 0.56. And what about the other locations? Sorry. So here, as you can see that in some other mode where I have got only a factor of safety of say 0.88, you'll find that buckling is experienced by the web at all other locations. And these calculations tells me that yes, internal stiffness are very much required. So accordingly, let us go ahead with the modeling of this internal stiffness. So that's why the stiffness are to be modeled in a logical way. You cannot just model it in any way you like. Okay, so let me just zoom it. It's good enough. Okay, so now let us. So now what I'm going to do is I'm going to model stiffness in this region and also model stiffness in this region. And a preliminary calculation has shown that no stiffness will be required in the center portion. However, if the designers feel yes for adding the factor of safety, he can provide at some other say nominal distance. For example, he can provide say 3 stiffness here at 2000 mm. Anyway, I have not modeled any stiffness in the center portion. Now I'm going to model some internal stiffness in the left portion. That means between the load stiffener and between the bearing stiffness in this zone as well as on the right side zone. So let us go in the same way. So what we do is we select the member first and go out to the operation. Okay, go to that transverse stiffness, and it has generated some stiffness for us. So the thickness, okay, obviously as it's an internal stiffener, what I will do is that I will go for it's an internal stiffener. I will go for some a little bit smaller thickness. So maybe 8 mm should be good enough. Both sides, I agree, it's okay. And then what I can do is that I have got as 275. Then the X position. So the first I want to position what we call as the rightmost part. So I'll keep it at 19 to 50. 19 to 50. Okay, the first internal stiffener will start at 19 to 50. And obviously here again, I don't want that, I want to save my material. So I will keep only for 150 mm, not for the entire flange width. And then here repeat count. In the repeat count, what I will do is I want 8 such a stiffness. I have computed it. Okay, 8. And then it will ask you what must be the delta x. And in this delta x, what we'll do is that we'll keep it as a minus 750. So because I want to move towards the left, so minus a 750, and this should provide you the required stiffness. Look here. So we have modeled the internal stiffness. This internal stiffness, let me just zoom it. Okay. So 1, 2, 3, 4, 5, 6, 7, 8 internal stiffness we have modeled. Okay. And remember that these are available on the other sides also. Now, in a similar way, what we do is that we will also generate the stiffness on the rightmost part. That means in this particular part. Okay. So we'll follow the same procedure. There is nothing new. Select the member first. Okay. And what you do is that you go to the operation, you go to the stiffness, and obviously Idea Statica has generated some parameters for you. So you can see that these stiffness are being generated. See stiff 1, stiff T1, T2, T3, T4 like that. So the thickness obviously will have 8 mm only. So it must be exactly similar to the stiffness we have generated on the left side. And if we require it on both sides, and you can have it on S275. Okay. And the position, you can keep it as a 750. The first position 750, we can cap it. And then what we can do is that we can keep it a width of say 150 mm. Okay, we'll keep it as a 150 mm because we want to save the material. And just like the other case, what we do is that we'll keep a repeat count of 8. Okay, so we'll keep it as, you can see that one is already generated here. I want to just copy it 8 times. okay, and it will ask you what exactly is that delta x, what's the spacing over which you want to copy it. So you can copy it, say here plus 750. So here delta x and keep it as a plus 750, 750. So you'll find that yes, it's being automatically generated. Okay, so means that we have generated all the stiffness. Okay, all the stiffness. Okay, all the stiffness are being generated. So now we are ready for running the calculations. Two calculations have to be carried out. One, what we normally call it as the MNA, that's the material nonlinear analysis, and second one is the LBA, that's the linear buckling analysis. So this analysis will take some time. I have noticed they take almost as much as 30 minutes on my laptop. So I'll just proceed for showing you the salient results of the developed model. Yes, our analysis is over. We have carried out both the MNA as well as the LBA. So first, let us review the results of the material nonlinear analysis. Here I have plotted for you what we call as the internal forces, the distribution of the inner forces, and it is My, that's a major moment. And you can see that as expected, we have two concentrated loads here. So we'll find that the moment, the bending moment is almost, you can see that it's a uniform here. There's a small variation. So the maximum is of 5963. And if you do a hand calculation, you will find that yes, there is some difference of 10 percentage. Maybe the because of the way in which Idea Statica obtains it from the analysis. So, and here you can see that as we have modeled a hinge here, the moment is acceptable, is almost zero at this edge. So this is okay. And similarly, we can also obtain the shear force distribution also. So it is important you review this, especially the minimum diagram, and see that the values are acceptable to you. And this ensures also that the loads are being properly applied and they are also applied at the proper locations. Okay. So this is about the Benny moment diagram, and here you can see that it's a long plate girder, 20 meters, and the depth is 1200. So in order to make the visibility a little bit more efficient, what I did is I have just kept mesh and the deformed options off here. So now let us go ahead with the strain distribution. Okay, let us see that which are the portions, because we have seen that from this analysis, the maximum it is 2%. Okay, so it takes some time actually to refresh the screen, maybe because of a little bit larger measures involved. Okay, it takes some time. So now, as you can see that here, if you see the right side, you can see that AM1. So the analyzed member has got a maximum strain of only 0.2%. Okay, but you may ask me then why it is showing say 2%. Here 2%, but this is not relevant to our AM1, that is the analyzed member, which is the plate girder. It is at some other locations which is not that much relevant for us. Let us see which location it is. So you can see that it is, yes, it is at some RM5. Okay, it is some member which is used for the restraint. So we are not worried about that. It's anyway it's 2% only. So anyway, we find that the top flange is the maximum strained portion, or obviously a maximum stress portion, with the maximum strain observed being 0.2%. And this is obviously less than 5%. It's acceptable for us. So let's just zoom it a little bit. So you can see that yes, there is a small portion over here, okay, which shows the strain. So I have to just zoom it a little bit. Yes, you can see that towards the center, there is a strain concentration of 0.2%. That is acceptable for us. There is no issue at all. Now let us go for the stress check. Okay, that will tell us the distribution of the stresses, okay, across the plate girder. And here it is very important that we check the stresses at the critical locations. Here, when I say the critical locations, I mean as far as the plate girder is concerned, one will be at the midspan and the other one will be at the support. And at these locations, we should ensure that yes, the stresses are within the permissible limits. Okay, and we did all the possible. Okay, to ensure that the stresses are within the limits. Look here. Yes, this is the distribution. So this is your central portion, right? And so here we find that extreme edges as expected. The stresses have gone to, let me just bring this a little bit down. Okay, let me So just because, yes, as you know that 275 we have used it as 275, and we can see that the flanges are being stressed to that level, and even the stresses are spreading towards the web. And but we find that in this zone, you find that in a particular rectangular zone, okay, the stress distribution is constant. The reason is simple: the bending moment will not vary that much. And we also find that towards the web, towards the web, the stresses are getting diminished. It is going somewhere in between 0 to 50, and this is our expectation also. Okay, and then now let us see some other concentrations where the stresses are likely to exceed. Obviously, one such location is the support. Look here, you can see that. Yes, at the support location, okay, we find that there is a large stress concentration to the total of 275. Maybe that to reduce this, we can plan one more stiffener in this zone, okay, so that may reduce, okay, that may reduce the effect of these stresses, and then we find that the stresses in the other regions are well within the limits, okay. So that is all about the stress distribution. Now I would like to show you what will be the maximum deflection under the service loads. Okay, so obviously the editing of the loads in the service section, it was not included in the tutorial as it consumes a lot of time. So I have done it in some other load combination known as LE2. So let us see what is the distribution profile or the deflected shape of my plate girder. Obviously here I need to make my deformed shape also on. So let us wait because it takes a lot of time. Okay, so you see when I ask for some query, it hangs on for some time. You can see that yes, it hangs on. So what I will do is that the figure comes after my plate cutter comes. Yes, this is my plate cutter. What I can do is I can keep this deformed on, and the deformed also we are interested in the deflection or the deformation in the z direction. So accordingly, what you can do is you can press use it. Okay, so press use it also. Let the screen comes. It takes some time. We need not be panic. It takes its own time. So now user has already come. So now let us see what will be the distribution of the deflection, right, under the service load, because we have got a plate girder of 20 meters. So the deflection checks are also dominant. Normally, in many cases, once you respect the much nominally used L by D ratio of say 15 to 20, you will find that there are not much problems regarding the deflection. So as you can see that this is a deflection profile. So this is a deformed one. So I don't want to use the meshes here. Let me just zoom it a little bit so that I don't want to change the scale also. So you'll find that here maximum deflection is 42.4, right? And that is at the midspan as expected, and it decreases towards to zero near to the supports. Okay, and so this deflection 42.4. So if you are having, for example, if you're considering a plate girder of say 20 meters like this, and a commonly adopted deflection of say L by 250, the maximum allowable works out to be around say 80 mm, and here the actual is only 42. So this is acceptable. So the deflection profile is acceptable. So this is all regarding our the material nonlinear analysis. So okay, fine. So M&A result interpretation is over. Next one is the linear buckling analysis. So what you do is that you just select this icon, LBA. Okay, fine. So now let us just investigate what are these basic buckling shapes. So please ensure that LE1 is our design load and LE2 is the load corresponding to the serviceability. So obviously for LE2 you have got a larger factors of safety, and we are not interested in LE2. LE1 is our design load. So look here. So inspecting this, we find that we have got the minimum factor of safety against mode 1, that is 1.35, and which is the mode shape. Look here, this is the mode shape. Okay, so for example, what we can do is we can also keep this deformed so that it gives you some kind of a visually pleasing appearance for the mode shapes. So take some time. Okay, so let me just keep it to say, for example, say I will keep it to say 10. So keep it as a 10. because I have scaled that deformation 2 times. Okay, that is up to 10 times, so that you will be able to see how the deflection, and to see the buckling shapes, ensure that you press the UI button also, because we are interested in the UI. Now look here. Okay, you can see that yes. So this is the critical mode shape for us. That means the buckling is critical in a panel that is very near to the support. Okay, so you will find that yes, here the large deformation, okay, is centered around this location, and you can also just rotate this and see that yes, some bulging and all, right? So this indicates that as far as our design trigger is concerned, from the buckling criteria, the critical zone will be the zone or the panel that is very near to the support. Okay, so this is our judgment number one. Okay, so you can see that yes, just because I have made it to 10, it's just showing you something like a, so okay, what we call as a depressed portion. So now we'll just see. So these are the critical one because we have got only a 1.35 factor of safety. 1.36 means obviously it must be a portion that is corresponding the similar panel zone that is corresponding to the right support location. Let us just see it. As I already told you, this will take some time. So this see a detailed investigation like this, it provides a lot of confidence. Look here. So you'll find that yes, the buckling is critical here also, very near to the support panel, and we have got only a factor safety of 1.36. It is greater than 1, there is no issue at all. So now that's all regarding 1 and 2. So where we have got, and we have got also 1.37 and 1.38. That is also critical. Let us see which are these locations. So we have designed it in such a way that the buckling is critical, is almost in all the zones, but we have got a very good margin, say 30 percentage. 30-35%. Let's see which are the other zones. Yes, so look here. This is another zone where my buckling is critical. It is very clear because here I have got a load also. You can see that yes, my buckling is very critical in a panel zone that is up very near to the applied loads. Okay, and there in 1 and 2 it was very near to the support reaction. So here you will find that and now coming to the fourth one, obviously this should corresponds to the one that is corresponding to the left side of my applied load. Let us just see that for the fourth mode. Okay, so you can see that. Let me just you see a similar one. Okay, you are having the so very near to the applied load, you are having another buckling zone. Okay, so the buckling form. Now coming to the fifth one. See, let us see the which is the fifth one, and we have got a larger factor of safety, 1.5. So we don't have any, we are not facing any kind of a problem just because we have not provided any kind of a stiffness in the interior portion. Okay, the center span. Yes, look here. So this shows as very interesting one. Okay, means that this web, it is just moving like a water wave. Okay, here I have got a depression. Here I got a valley. It is so if you see a plan, it will be something like a wave. Okay, and this is the buckling that is expected in the central zone. And don't worry about this buckling. We have got a factor safety of 1.5. So this concludes that our design plate girder is good enough as far as the material is concerned, and is also good enough as far as the buckling phenomenon is concerned. So I would request you, please go through this. See, the Idea Statica member is a very valuable tool that must be productively used in such critical cases. For example, plate girder, and we have used in industry where Idea Statica member can be used for the gantry girders. It can be effectively used for large silo supporting equipments. You can investigate all kind. And to this plate girder, if I am also interested in adding some kind of imperfections, right now my imperfections are zero. I can also, because many of the international codes, for example, the European codes also tells you that yes, some kind of imperfection also to be incorporated. Take care of many other unforeseen things, misalignments, okay, the load application points and all. So, and that is now imperfection is put equal to zero. If you want to add some kind of imperfection, for example, 20 mm, 10 mm, you can also verify the girder. Maybe that if I add the imperfection, my plate girder may not be sufficient enough. Okay, so that's all about. So please ensure that you make first of all entering into the Idea Statica, make your concepts clear, make a lot of hand calculations, differentiate between what we call as the buckling caused by the compression, buckling caused by the shear, what are the possible locations of the buckling, and there is also a very important phenomenon known as a tension field action in the plate girders. So all these are very interesting things which are being well established through a series of laboratory tests. So the behavior of the plate girder is very well known to us, and Idea Statica is a tool that helps us to make our designs very efficient. And here we have seen that we have got sufficient factor safety of 1.5 and we have taken to the material up to 0.2 percentage. So that's all about this part. So thanks a lot. So please ensure that you read part 1 and part 2 of the tutorials together. Okay. If you have any comments, you can very well mail to me. Okay. Or send a comment through my YouTube channel. So that's all. So thanks a lot and have a nice day.